Gregory Stark. I've been contributing to Postgres for 16 years, off and on. In that time, I've also been a DBA, responsible for monitoring Postgres systems, fleets of Postgres systems. And I have complaints. And I have ideas on how to change it. So what I intend to present here is my plan for how to improve the infrastructure for monitoring. It might give you some ideas on how to monitor using the existing infrastructure, but my real goal is to advocate for a project that I'm embarking on, or hopefully get other people interested in to help with, to make Postgres easier to monitor and more well integrated with other monitoring systems. So what we're talking about here are metrics. It's part of the larger picture of observability. Metrics are quantitative measurements of the system. So in Postgres, that means things like how many sequential scans you're doing, how many index scans, how much time is spent doing different operations and states, how many times various events have occurred, like vacuums or deadlocks or conflicts and so on. I'm not talking about richer data, like that typically goes into the logs, or other kinds of monitoring that also exist but need a different type of solution. For Postgres, those metrics are available along with some of that other data in what are called the statistics views. You select from PGStat all tables, PGStat activity, PGStat BG writer. There's actually 44 of these views. Those views are actually implemented on top of functions, and some data is actually only available by directly using some function which returns some internal counter or state. So the way you access that data is you connect to the database through SQL, and you run queries. You run queries on these views. You typically have to join the views against catalog tables. There are agents that do that for you. So for example, with Prometheus, there's Postgres exporter. It connects to your database, and it connects to your database, and it runs various queries. It gets the statistics and the metadata about those statistics, which typically come from the catalog, and exports them to Prometheus. And I'm talking about Prometheus, but actually there's a whole suite of modern monitoring systems that have various pros and cons, but follow that basic model of having an external system that gathers all your monitoring metrics in effectively another database, but one more tuned for time series, one more tuned for running the kinds of queries you need to discover trends or discrepancies over time or across your fleet of databases or systems. This is sort of a modern approach to monitoring. It allows you to monitor your whole ecosystem, and you get much richer context for designing your alerts and designing your dashboards, instead of having a very Postgres-specific system and a separate operating system-specific system and so on. In theory, the things I'm talking about are actually applicable even to traditional, say, Nagios-style monitoring. It's about getting the data out of Postgres, and that's actually applicable for any kind of monitoring, but it's especially applicable to this modern style, because these systems like Prometheus or Datadog or CloudWatch or all of these different monitoring systems, they have their own model they want you to fit the metrics into, and they have their own their exposition format, the way they actually ship the metrics. So they all have this model of having an agent that pulls the data out of Postgres and formats it appropriately and ships it off. Typically, Prometheus is a very typical example, but its exposition format's actually being coalesced in there's I'm jumping ahead 2 slides, I'm sorry. But the Prometheus exposition format is becoming an industry standard. A lot of these other monitoring agents are now accepting that exposition format or something very similar to it. The open metrics format is basically the same format with additional constraints and some new features that they want to add. The point is, it's a very constrained format. It's a flat model that lists all your metrics in a very straightforward format. It's not a relational model like with Postgres tables, and it doesn't have room for other kinds of monitoring data. This is purely the quantitative metrics that this is catering for. For Postgres, that agent, the standard agent for Prometheus, but also for anything else using that exposition format, is called Postgres Exporter. So each site that uses it, when it deploys a Postgres database, also needs to deploy a Postgres Exporter alongside. You need to make sure that Postgres Exporter can connect to your database, that the authentication is set up, the networking is set up, that you have configured it to connect to the correct port, and so on. And then on the Prometheus side, that all of that information is mapped to the database that you're actually intending to monitor. And then you design your dashboards around taking into account how you've set that up, how you've arranged to run Postgres Exporter. When failover happens, when you add new nodes to your sharding or your replication network, you need to take into account how that was deployed. So this is from an earlier presentation where I presented how to use Prometheus to monitor Postgres. And what we're talking about here is basically this segment here, which is pulling data from Postgres by connecting over SQL to the Postgres statistics views and running queries. It actually runs additional queries that you can configure in a user customizable file to add additional queries, and those can pull from other views like PGStat statements or even your own applications tables and so on. And as an aside, like the whole advantage of doing it this way is you pulling in data from all different sources into the same place, and then you can design your dashboards and your alerts to use all that data. I want to replace Postgres Exporter with a different approach. So the problems with Postgres Exporter, the problems with having an agent, a separate process that has to be deployed separately, that has to be, that is developed separately, you have to deploy it separately, you have to organize the rest of your infrastructure around this split model. The 3 basic classes of problems that I've run into in the past is, first of all, it's operationally complex. It's on you to arrange that there's a Postgres exporter for every database, that it's set up correctly to be able to connect to your database, that you may have to maintain the mapping between the host and port that the exporter is running on and the host and port that the database that it's monitoring is connecting to. You have to design everything around that mapping and maintain that mapping. It's easy for those to get out of sync. And then when it comes time to restart things or update your custom queries, or even upgrade the agent itself, now you have to deal with, do you upgrade Postgres and the agent at the same time? You can you upgrade one on its own? And what is it going to do to your statistics? Your dashboards have to deal with multiple different versions of the agent's configuration on different sites, and then different versions of Postgres, each of which could have different versions of the agent. And it gets to be complex. And importantly, this is an overhead for each site. This isn't complexity that can be buried in the agent itself or in Postgres. Everyone has to reinvent the wheel here, which is what I really think is the heart of the problem. I also don't think this is the right architecture, because there's two other classes of problems. One is you're using the same infrastructure that the application is using to retrieve these statistics. You're using the SQL layer. You're using the transaction model. So you need to use you're using some of the same resources, the available connections in Max. You're using up some of the connections from Max Connections. You're using the same resources, memory, CPU, locks, and so on. And you're using you're connecting to a database, you're using transactions. I have some examples of where this actually causes problems for the monitoring and where the monitoring can actually cause problems for your application. And on top of that, in the end result has, even if everything's working properly, it means your data, the metrics, are going through multiple layers of reinterpretation. So the metrics are stored in shared memory in Postgres in some C data types, usually 64-bit integers, sometimes some other representation. To go into the PG stats view, it needs to be marshaled into a SQL data type of some sort. It gets retrieved by Postgres exporter, which is a Go binary. It uses Go libraries to interpret that data, and then it needs to render it again into open metrics format, which is a float. Each step along here is reinterpreting the data, and having multiple stages like that means you have multiple chances to lose fidelity, to lose context to lose context that is important for interpreting this data accurately. So I have an example. Well, I'm sorry. I have more detailed slides on each of those 3 points, but I've actually covered most of the points. So the operational complexity, as I said, even when it's working as intended, it's a headache. Everyone has to customize their dashboards around the way this mapping is done. I've seen problems where a failover occurred, but the agent was still connecting to the old database, which was still running and appeared to be functioning fine and just had low traffic. So no alerts were being fired, but it wasn't the correct database to be monitoring anymore. And the dashboards, because they have this baked-in concept of what the mapping was, were claiming this was the primary database that was being used. I've seen instances where a database was sharded, sort of sharded, where parts of the database were hived off into new databases, but the people that did that were unaware of how the monitoring was set up, so the monitoring was still monitoring the old schemas in the old database, not the new schemas that had been copied over to other databases. And I've also run into problems with version skew, where new queries had been added to the custom queries file, and the dashboards adapted for those new queries, but it took months until those new queries were actually rolled out to all the sites, and so the dashboards, it was a challenge to keep the dashboards sensible for sites that had both the new queries and the old queries. The resource contention, examples of the resource contention problems are that I've actually had in the real world include When we neared transaction wraparound, and the Postgres exporter could no longer connect to the database because older versions of Postgres blocked all connections when you were near wraparound. I've also seen problems with max connections where you have super user reserved connections, but it's actually a best practice to not use super user for Postgres exporter. So Postgres exporter mitigates that by keeping connections open all the time. But when you restart it, it still has to reconnect. And if you're nearing max connections, you can run into problems. There's other circumstances where it will reconnect and cause problems. Keeping database connections open all the time causes its own problems because it needs to be connected to every database. An SQL connection is to a specific database within your cluster. That's using up a good number of connections as well, and it's keeping them connected all the time. And I have a slide about that. Also lock table, any queries that access a table that's locked will block, and typically people will have queries in the custom queries that do things. What we had was PG relation size for all our tables. Well, a new feature in the application was using a lock table on a zero size table as a semaphore to serialize part of the application. That blocked PG relation size. And then when there was a problem with the application that kept that lock for too long, we lost all our metrics. And this is exactly when we needed the metrics to go and investigate what's going on causing this slowdown. We lost everything. So I did some, and the data fidelity problems. So just two examples of, data fidelity is sort of an abstract problem that I'm arguing is an architectural problem, but two examples that I think spell out the issue is timestamps, which internally are stored as microseconds in an integer from one epoch. They have to get translated to a timestamp data type for the stats views. Then they get read into Go using a different time zone library, possibly different time zone interpretation of time zones. Hopefully, I believe Postgres exporter sets the time zone for its connection to GMT. So it's trying to avoid these problems. But this is the kind of problem that I would not be surprised. I mean, this is kind of cheating to say I think it's a possible problem. I'm implying there's problems when there's probably this specific problem has been worked around. But you're relying on Postgres exporter being very careful about things that are quite subtle and require understanding internal Postgres representations in some cases. I doubt it's actually retaining microsecond precision, for example, in the timestamps that it's eventually exporting as metrics. I don't believe it has any issues with time zones, but you could definitely see how easily there could be a problem. Most of Postgres metrics are kept as 64-bit integers, but OpenMetrics, for example, uses floating point. Floating point can only have a precision of up to 2 to the 53 values. For counters, it would be better for it to be wrapping at 2 to the 53, so that when you have a counter, you're typically actually interested in the deltas, how quickly that counter is incrementing. In some cases, for things like deadlocks or vacuums, 1 is a perfectly interesting value for the delta. But if you I would be surprised if you reach 2 to the 53 vacuums or deadlocks, but for things that are measuring memory or network, you could get large numbers and you could start losing precision where all the derivative, the deltas are all truncated to 2 or 4, only even numbers effectively. So I think going directly from the shared memory, well, I'll get into what I plan to do, but there's a better architecture that you can't eliminate these problems, but you can minimize them. You can choose an architecture where you're not compounding the risk of bugs at each step here. So this is a typical dashboard. I'm actually surprised it's more legible than I feared. That's good. This is the most popular Postgres dashboard on the Grafana website. There's actually a mix-in, which I should probably talk about, which I don't have slides for. That's like Grafana's way of, there is a mix-in that might be a better representation or better example, but this is the most popular one on the website to import. It's really designed around monitoring a database. So you could, on the top there's drop-downs. You can select from the various databases that you have metrics for, but you're looking at one at a time. This is they call it a wall of graphs, a glass panel where it's the dashboard for watching a single Postgres database. But specifically, those drop-downs on the top, there's one, I've clicked on it to drop down, that lists the various databases that that you can bring up this dashboard for. But what it's showing you here is localhost :9187. Now, localhost is the person using the dashboard has to understand what this represents to actually use the dashboard competently. Localhost is the host that Prometheus is connecting to. That's not necessarily where the database is running, that's where the agent's running. And 9187 is actually the port the agent is exporting metrics on, not the port that the database is listening on. So you have to know, now usually people deploy the agent on the same host, but not always. If you're on RDS, for example, you might deploy it on an EC2 instance, so you have to know which RDS each EC2 instance has actually been deployed to run an agent for. So like, at least in the naive configuration, you have to know that like which host corresponds with which database host, and if that's the same, you still have to know which agent port corresponds to which Postgres cluster. Now there's ways of configuring Prometheus to hide that from the dashboard user, but that just shifts the complexity to whoever is configuring Prometheus needs to understand that and bake all that information. So it's better, but it's additional complexity that when you're setting up Prometheus for the first time especially, you definitely don't initially jump into. You typically end up with this. And then, oh, hey. Sorry, there's another, I lost a slide. Okay, so if you, well, okay. I'll mention it when, I might have a slide out of order. So the agent has multiple, if you have many databases, the agent will have a connection to each database. And I mentioned it keeps a persistent connection because that avoids a number of potential well, it's more efficient for one thing, but it also avoids problems if you reach max connections, if there's any authentication problems that it can't reconnect. But this actually caused me a problem when I was running this benchmark because now it has a persistent connection to all the databases. I tried running a regression test to get some interesting metrics. The regression test failed because one of the operations they test is dropping a database, which doesn't work because it has the monitoring agent has a persistent connection. And you can definitely imagine like trying to deploy your new application and having a migration in there that drops some old database that's no longer used and having the whole thing crash because of monitoring. That's an example of the kind of thing. So in an ideal world with Prometheus or any of these similar monitoring systems, even something like Nagios. In an ideal world, if you're writing an application from scratch using Prometheus libraries to instrument your own application, what you're told to do is set things up so that the monitoring software, and I'm going to keep saying Prometheus, but it's a stand-in for all of these things. M3, Datadog, whatever. The best practice is to have your application listening on its normal service port for these metric requests. So then you can configure Prometheus to go probe your actual application and ask for metrics. And then Prometheus reports these metrics associated with the host and port of your service. You don't need to maintain this mapping. You don't need to understand which host and port corresponds to which service address, the database address. So in an ideal world, you'd arrange your Kubernetes or your whatever cluster management software you have to start up Postgres and add that Postgres address. It knows it wants to be running a Postgres on this host at this port. Add that to the service database or whatever system you have for discovering services, and you're done. The monitoring system knows there's a database running at this host and port. I'll start monitoring it at that host and port. And then you can do things like add dashboards, canned standard dashboards or alerts, and they would work out of the box. They would understand. Your drop-down there would have your actual database host. You could have a higher level dashboard that lists your databases. It would be listing your actual database addresses, not something else that needs to then be customized to map things to the correct addresses. Your alerts you could have alerts that compare things like the operating system metrics you're getting back and the database metrics you're getting back, but you could compare them and understand, like take the host name from each and understand that this database is running on the same host that these operating system metrics are coming from because it has the correct host name in it. You could have things like alerts on networking that this port is open on your router because this port is a service that, or blocked on your router, as the case may be, because it's a port that appears in the list of services that are running and in the metrics you're getting back from your networking stack. And it's the same port. You don't, and these things could work out of the box. You wouldn't have to write them. Each site wouldn't have to write custom designed dashboards and or take that dashboard from Grafana and then immediately start customizing the dropdown to actually show something more meaningful for them, or the list of databases to show something more sensible. Also, the metrics should, the whole custom queries thing where you can add your own queries, in the Prometheus world, it's considered an anti-pattern. And the reason why is this same thing. You can't have canned dashboards that work out of the box for everyone if they depend on first, by the way, you need to go add this query to your custom queries. And if you have a different dashboard that requires a different custom query for the same data, now you need to deal with resolving the discrepancies between them in some way. You need, in an ideal world, you start up Postgres, there's a standard set of metrics that people can rely on having standard set of labels, a standard set of names, they're always there. They would be the same. So if you have Postgres 10, you have the Postgres 10 metrics. If you have Postgres 11, obviously I'm not going back in time to add things to, let's say if you have Postgres 15, you have the Postgres 15 metrics. Postgres 16 would have the Postgres 16 metrics, and if you deploy a dashboard, it knows either you'd have a dashboard that says this is for Postgres 16, or you'd have a very clever one that would actually be able to manage both sets of metrics, but it doesn't need to manage Postgres 15 with the old exporter or the new exporter, or with or without your custom query, on Postgres 16 with the same queries but different data because Postgres 16 has different columns. You want something with consistent data that works out of the box, which allows dashboards and alerts to work out of the box so that everyone doesn't have to roll their own. And now is a good time to do this for two reasons. Postgres 15 has a new infrastructure for retaining these metrics. It's managed in shared memory. That makes it more efficient, but also makes it more feasible to abstract away some of the complexity here, so that the built-in equivalent of the agent would be able to handle new kinds of metrics without having lots of custom code for every different kind of metric. There's still work to be done in that area, but it's now much more feasible to see that work happening than when you're layering it on top of some of the oldest code in Postgres. The old method was clever, but complex and challenging to work with. The new code is much more amenable to adding abstractions. But also on the monitoring side, Postgres the community doesn't like tying Postgres to specific other technology stacks. Postgres likes to be very agnostic about being very extensible and making it allowing it to be very agnostic about which technology stack it integrates into. That's worked well for Postgres over its history. It's meant that it's been very agile at moving to new contexts. But now is a time when the industry is kind of settling on not necessarily Prometheus, though it's very popular, but the Prometheus model, the model of having this very simple text exposition format, the flat model of here's your list of metrics. The metrics have labels. The labels are very simple text label. The exposition format itself is being standardized, but if we wanted to support multiple exposition formats, they're probably going to look very similar to this. So it would be reasonable on the Postgres world to support something called open metrics. It sounds very open. But also the code, we're not really painting ourselves into a corner. It'll be useful to have that code, even if we later have to add new exposition formats. If they're following the same model, we'll still have a path forward. And these tools are incredibly popular in the cloud deployed world, whether it's like public clouds like AWS or GCP or Azure, or just loads of companies have these in-house database as a service systems, and this is the model for monitoring applications deployed to things like that. So, as I mentioned, Postgres has a new shared memory stats gatherer. So instead of having a separate process that all the backends send their stats to over networking, it's now managed in shared memory. And that means it's actually fairly straightforward to have a, So the way the stats views work today is you connect via SQL, you run a query, that calls a function. That function then looks into this shared memory data structure. It's a hash, there is a hash table involved where it looks up the stats that your function is looking for. So all those stats views, they actually work in a way that makes sense from a database point of view, but not necessarily from a monitoring point of view. They all work by, well, I don't know all, but generally they work by looking at the database catalog for the database you're connected to, getting a list of objects that you're querying, and calling the function to look up the stats for each of those objects. I mean, it's SQL, so it's a join. I mean, it makes sense as a way of writing a query for the view, and it makes sense if you're in the SQL engine to run this way. But if you're a monitoring agent and what you're actually looking for is stats on everything, you're kind of doing it the complicated way. Instead, like, if for a background worker accessing shared memory directly and exporting stats directly, we can, what I've implemented was I just look at the hash table and iterate over all the objects in the hash table and export those stats. I don't care what catalog object they correspond to. I'm not selecting only some catalog objects. I want all of them anyways. So each stats object in that hash table has enough metadata that I can export the metrics. I know if it's a table or a replication slot or a function, and I know what stats are there, I can just export them. I don't need to start by doing complicated transactional semantics to scan all the catalog tables. So this is more efficient, but more importantly, it's avoiding all those resource contention problems that I described before. We don't need to lock catalog objects. We don't need a transaction. We don't need. Someone I mentioned this the other day said, like, your database is ACID compliant. It has ACID transactional semantics. Your monitoring maybe doesn't need to be. And in fact, it's kind of a detriment for the monitoring to be ACID compliant. You want the most up-to-date raw data out of that shared memory anyways. So I implemented this, and it was actually easier than doing it the other way would have been, and avoids all these problems. So what I implemented is a background worker. You can set it to start when you start up Postgres, or you can call a function to kick it off on a given port. And it runs a little web server inside. There's a C library for very minimal overhead web server. That means it's running on a different port. So going back to what I said before about the ideal way things should be running, ideally it should be responding to metric requests on the Postmaster's database port. That will not be easy. So right now it's running on a separate port, which is really unfortunate. When I say it won't be easy, right now there's like a couple fundamental reasons why it's basically impossible. But Postgres protocol has the server speaking first. The client connects and waits for the server to identify itself and then starts talking. HTTP works the other way around, and there's no good way of having both of those run on the same port, because you can have timeouts or something, but it's not ideal. There is possibly in the future interest in having database connections run over HTTP. That would be really interesting for a number of reasons, service mesh reasons. As a number of reasons, actually, other reasons as well. So like this may be a problem where other people, it's more important for other reasons anyways and gets solved for other reasons, and then it just makes the world better for monitoring as well. Passing connections from to an existing backend would also be an engineering challenge. So there's also a whole bunch of sort of really boring bike shedding issues, The metrics themselves are have grown over the years, and their naming is really not consistent. They're not consistent. I had kind of envisioned that using the internal names would make it suddenly solve all this and make it all consistent, but the internal names are also not consistent, and not consistent in different ways from the way the external ones are. So it's a bit of, there will be interesting things to do there. For now, I'm trying to make them more or less backwards compatible, but it is a good time to clean up some of that. So actually, here's the slide I missed before. This is showing you, like, when you run Postgres exporter, it was holding all these connections to these existing databases. And here's my new background worker. It's just one session, and it's always there. It doesn't need to connect over the network. It doesn't need authentication set up. So it's reliably connected to the backend shared memory, whereas these, if they get disconnected, need to use a connection out of max connections to reconnect. They're holding that database that the regression test tried to drop. This is one of those sessions, was the one that caused it to fail. And that's, yeah, so this is an option here, auto-discover databases, where, like, if you create a new database, it will discover it and create a new connection, which obviously causes its own problems. But one of the things, aside from that, it means it's querying PG database. So, I don't know, this is a graph using the Postgres exporter and the equivalent graph with mine. One thing to note is it doesn't actually have the table names, just the ID numbers. That's another issue. So this is that same graph. And you'll note that Postgres exporter had this window when the metrics were missing. Now, I kind of cheesed this. I did lock table PG database to trigger that. And that auto-discover databases is running a query to discover new databases. If you lock, now, the reason I say this is cheesy is because, like, if you have someone with super user access running around locking catalog tables, they could be doing all kinds of havoc. But this is the same problem we had with that semaphore table. The built-in Postgres exporter doesn't, like, go access all your user tables, but everyone adds queries like that to custom queries. So as I said, we don't have access to the object names. Those would be in the catalog, and I can't access the catalog. So there are solutions for that. The problem there, I propose just adding, like, the most obvious problem is just add that to the shared stats infrastructure. But it would add a lot of overhead. Like, it would make the stats data much larger. So there's a lot of resistance to that. Also, I'm not even sure that's the best solution. Different databases can have different encodings. And if we're going to stuff these all into shared memory, like, and some of them are in one encoding, some are in a different encoding, it's not really clear to me, and that's like, necessarily the best solution. And then, yeah, like, if you rename an object, you don't want to be if you rename an object, it'll break your time series if we put that name on the time series. There's other solutions that may be better in the long term, but they're hard. Definitely the easiest thing is to somehow ship the names either in shared memory or pulling. I have in mind to go query all the catalogs in, like, I'd say separate thread. It wouldn't really be a thread, but, like, and just keep those as hints that we use to annotate them, but not part of the critical loop that's actually fetching the metrics. Some of the metrics that people really care about, like rel frozen XID, were probably one of the most important metrics to be monitoring. It's not really a metric, but one of the important things to turn into a metric to monitor is actually not in the stats. It is in the catalog. It's on PG class. So that definitely needs a solution of some sort. I don't have one yet, and I'm definitely open to ideas on how to monitor things like that. Some of them we can probably move over to the stats or mirror in the stats. Like, here, the authoritative data is in the catalog, but here's a metric that's tracking it. something like that. And yeah, people do really want their custom queries. I really strongly believe it's a bad pattern to have those custom queries be serving the role of exporting basic infrastructural metrics for Postgres. But people do need their custom queries for monitoring their application, for monitoring their the way they're using the database that might not be, strictly speaking, database monitoring. So there probably is a role for some sort of exporter whose job is to connect to databases, run SQL, and export data. Things like your QDepth. That's your application it's really monitoring. But it is a handy way to monitor it, is to go run a database query. Often people will add those to the application. That's probably the right solution. But often, you have different roles. The DBA might be a different role from the developer, and he wants or she wants to run database queries to go monitor things like QDepth, and it's not it's not necessarily the developer's job to do that. But that could actually be a generic database monitor. It doesn't need to be Postgres specific in any way. So you could, and that actually could make it a more, there are existing agents that serve that role that are just SQL. They use like the Go generic SQL library and connect to any database and run queries. And I did make a really I'm not sure I said it in such a dogmatic way here, but there was a point there where I said all the metrics should always be reliable. Postgres 15 has the Postgres 15 stats, and everyone has the same stats. In the real world, there's going to be people that don't want to leak their table names, for example, or even the table sizes, or even the number of connections per application. Like there's environments where you're worried about leaking data that most people would not consider a leak. So there would need to be GUCs to enable and disable these metrics, and probably there's a big question about what volume of metrics is appropriate. Some people have databases with thousands of tables, and other people have databases with one critical table. So the people with one critical table want all the detail they can get on that table. The people with thousands of tables probably just want a higher level view of their database. They're not going to be looking at, they're not going to be able to deal with the full detail of metrics on all their tables. So I really want to keep the configuration here to a minimum where you just turn off and on the metrics and decide at what level of detail you're willing to export, not turn off and on individual metrics on individual objects. Because once you get into there, you can't use a canned dashboard. It won't work out of the box if it's going to depend on metric A and B, but not C and so on. In the future, this is only a piece of the puzzle. The cliche is there's 3 pillars of observability: metrics, logs, and tracing. And this is metrics, but in the future, we also should be exporting logs in a structured format with this, and ideally tracing. And those things need to be seen as part of a whole, so they would have the same labels as the metrics. They would have the same, if you log an event, and it has some associated number, like quantities in there, like the amount of tuples that the vacuum cleaned up, that needs to be also represented in a metric with the same name, labeled with the same, like, you don't want like relation name in one and table name in another, or ID in one place and OID in another. In an ideal world, you want to be able to go from like tracing, my application is causing a problem with this API call. Tracing tell you, oh, well, you're doing sequential scans on this table. Okay, show me the log entries for that table by like one click. Click on that table on the trace, go straight to the metric for that quantity that you're looking at. Oh, yeah, it's definitely a problem. There's lots of sequentials. Click on that, find all the errors that occurred on this table. The same label is carried all the way through, so you can answer questions in one area, go from questions in one area that when you get the answers, that leads to questions that you want to be able to pull all of these together. That is my last slide, and the out of time slide came up just dead on at the same time. So if you have any questions, I'll be around. I don't think there's, yeah, I used all the time, I think, so I think I have to tell you to catch me afterwards outside. Okay. So if you want to take a few questions, then is that what you're saying? There's a microphone.
How much of these are ideas, and how much of them have you tried to implement, and where are you?
I posted code. The code is, I'd say, a proof of concept. It runs, it listens, it reports metrics. I showed you graphs, like that lower graph is coming, it's in Grafana. Well, they're both in Grafana. The lower one is using metrics coming from my code. That said, I haven't, what I've done is exported all the metrics that are in shared memory now, but I haven't gone through all the PGStat views to make sure that, I mean, I know there's metrics that are, it's early days. I have something that's running now, but it's not really production-ready code. And in particular, the metrics, the names are not consistent with the old names, and there's definitely some that will need discussion. And there's a whole suite of metrics that are not in shared memory that either I should be fetching on my own or should be moved into shared memory. Things like all the not the replication stats, but like all the things where you, like PG log wall position, things like that, where there's special functions for it, they're not there. The existing agent queries, things like PG stat activity, it's doing aggregation on that. It's doing extra work that isn't just exporting data from shared memory. So some of that I need to reproduce because it's going to be necessary, and some of it should, there will be work to do of the form of convincing people that they don't want what they think they want. That's a challenge.
Awesome. All right, I think we'll wrap it up because we are over time, but
okay.
Thank you very much.